Questions? Nothing? All right. So we stopped last time on sums. And the idea here is if I would sum up from, say, I equal m to n of the a sub I is just simply do m a sub m plus a sub n plus 1 plus up to a sub n. So what we're doing is we're just adding up. Add the terms of sequence. So obviously we need to know sequences before we know sums. And we would just simply add up those components to be able to get a sum. Now, how you actually do this is, one, just simply literally add. Just write down the numbers and just simply add them up and we would get to our solution. Other techniques in terms of going through it is to not just simply take everything that you see and just simply add up all those values, but rather try to approach it and say, can I turn an ellipsis that I see in terms of a pattern to figure out the end result and try to eliminate the pattern. In other words, what I'm talking about is that whole ellipsis thing right here, right? I have an ellipsis here which has some unknown number of terms that I'm going to have to worry about. An example of, say, eliminating a pattern would be, is there another representation for 0.9999 dot dot dot? If I would look at this in terms of an actual, yeah, it's 1. One of the questions is why. When we look at an infinite number of decimals, decimal representation is just simply a sum, right? This is 9/10 plus 9/100 plus 9/1000 plus, right? Dot, dot, dot. Now I'm just simply going to be adding these guys up. If I look at that, I'd like, okay, please add these all. Well, all right, I have an ellipsis here. I don't know necessarily how to add them all. So how could I get rid of them? Well, I would need to subtract a like thing. And when I look at this, I would notice that for each of these, this is just a geometric series, right? This is 9 times 1/10 plus 9 times 1/10 squared plus 9 times 1/10 cubed plus etc. It's just a geometric series. It's a constant in a base being raised to a power. Now, if this is what I'm interested in, and I'll just simply call it S, I would like to sum this entire thing up. The problem is my literal add has that ellipsis. It doesn't actually ever stop. But if I would look at it and say, all right, what would happen if I multiplied everything by a 10th? Or better yet, what if I multiplied everything by a 10? I would say, how about 10s? Make life a little easier. What would be my first number? 9 plus everybody loses a 10th. What do you notice about that? What is that block of stuff? It's just S. You know, all of that is just simply S. So really, what have I shown? That 10S is equal to 9 plus S. Same thing. So what I've done is I've taken, both sides have, inside of S is the ellipsis, right? There's an ellipsis in both of those S's. But I just write it as S, and what happens when I subtract both sides? by s. I would just simply say, oh, that's 9s is equal to 9, s is equal to 1. So this is a common technique in terms of taking problems out, and this is the common technique of a geometric series, is multiplying it and trying to say, don't represent it as an actual addition, just simply take it, multiply it. Oh, look, it's the repeat of the same thing, and so I can use subtraction and solve my problem. And so this is the same thing as 1. So 1 is equal to 0.999 repeating. Actually, one of the things that you could actually show is from this. All terminating decimals. What do I mean by terminating decimals? It's a problem that has an infinite number of zeros, say like 1.23, 000, right? That's a terminating decimal. It has an infinite number of zeros. All terminating decimals actually have an infinite 9 version. In other words, that's 1.22999 repeating. Those are equal. In other words, 3 is the same thing as 299999999. So it ends up being that fractions, right? Terminating decimals are actually a rational number. For the terminating decimal rationals, there's 2 ways that you can write them. One with an infinite number of zeros and one with an infinite number of 9s. And they're equal to each other. This will actually lead to an issue. When we did the definition of rational numbers, we said rationals have one representation, right? If I had things like 6 divided by 15, that's not a rational number. We would cancel out the common factor of 3 and get this as actually 2/5. Right? We only allow one representation. So this automatically leads to somewhat of a thing that we have to think about. When I said all real numbers can be written in decimal form, it had a repeat in it that we didn't know about. Like I had 2 decimal forms for one number. Well, what if I require uniqueness? I'm going to have to throw away one of them. Like we'll say that decimal forms are allowed except for the infinite number of 9s. If you get an infinite number of 9s, we do not represent it. We rather write the infinite number of 0 form of the terminating decimal. So now we actually have a larger group. Decimals are larger than the real. In a way, they're larger than the reals because they all have 2 representations. We would say, oh, wait. We have 2 versions of that. Well, we're not going to allow that one. It's kind of the idea of naive set theory. Get an issue, just say not that. And we're good. All right. So dealing with sums in a lot of ways are how do we add them up without actually adding them up? And so some interesting sums that we need to be able to do. The first would be the telescoping. The idea of telescoping sums is it looks a series, say from I equal, it doesn't matter what the bases are, say from 1 to n. But here I have a sub I, and I subtract, say, I don't know, a sub I minus, say, 2. Or a sub I minus 1. The idea of a telescoping sum is we subtract a term minus a previous term is the entire thing that we're trying to add up. Say an example of something like this would be, what would be the sum from I equal 1 to 10 of I squared minus AI minus 1 squared? Both of these are something squared, except what's happening is we're doing a variation of the 2 terms. And if I would say add this up, all right, if I would actually add it, okay, this would be equal to, if I use normal addition, we would just simply say, okay, plug a 1 in. That'd be 1 squared minus 0 squared. That'd be my first term. Plus, now we plug, so that was I equal 1. I equal 2, what would I get? 2 squared, just write them as a square. 2 squared minus 1 squared, and that was I equal to 2, plus I would get 3 squared minus 2 squared, and that was I equal to 3, plus, and we can continue on until we get to I equal to 10. And I equal to 10, we have a 10 squared minus 9 squared. Is everybody okay with that? And I have some middle terms. So if I would actually add this up, if I said truly add, I would have that this is equal to 1 plus 4 minus 1, which is 3, plus 9 minus 4, which is 5, plus, and the next one would be 16 minus 9, which would be 7, plus ellipsis, and what would be the last one? What's 100 minus 81? 19. And so if we would look at this pattern, what am I supposed to add? Add up the odds from 1 to 19. Okay, and if you'd want to do that, okay, before 19 would be 17, and then plus 19, and we can kind of look at it and say, all right, well, what is this? Well, I can cheat a little bit. That's 20. That's 20. And then I would have 20, 20, 20, 20, 20. And so if I would write all these guys, how many 20s would I have? If I wanted to do this by hand. So 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus, that doesn't look like a 17. 17 plus 9. And am I missing any odds? No. So that'd be a 20 with 19, a 20 with 17, a 20 with 15, a 20 with 13, and a 20 with 11, right? How many 20s did I have? 5 20s, and so the answer is 100. That was literally adding it, right, without pulling out a calculator. And this is also a really good technique for how do you add. Don't look for shortcuts. Do not do 1 plus 3 plus 5 plus 7. That's kind of a pain, right? Look for things like usually low and high and see if a pattern happens. Always try to do additions that make your life easier by doing multiplication, right? On the other hand, the idea of this thing being a telescoping sum, is there a difference? For telescoping, I really didn't need to do this. If I look back at the original, I had this whole 1 squared minus 0 squared plus 2 squared minus 1 squared plus 3 squared minus 2 squared plus, the last one was 10 squared minus 9 squared. The one before that was 9 squared minus 8 squared, right? If I look at this and I didn't add them, I would say timeout. Let's use the associative property of addition, and notice that 1 squared minus 1 squared, 2 squared minus 2 squared. What do I notice is subtracting? Between any neighboring terms, who subtracts? The left of the first term and the right of the next term. So here's two neighboring terms. The left of the first term subtracts with the right of the other term, like here, that guy, there, and there. So who's all going to subtract if I do this? Everybody except, who's the only people that are not going to subtract? 10 squared and 0 squared. Everybody else will. Why is this called a telescoping sum? Well, if you've ever seen a pirate telescope, like in the movies, like what do those telescopes do? They collapse. What happens when I have a term minus another term? Lots of subtraction. This entire thing will collapse, and this would be just equal to 10 squared minus 0 squared, which is equal to 100. Hey, same answer. What happens on telescoping sums, for any sort of telescoping sum? What you'll notice is if I would have, say, the sum from I equal 1 to 100 of I 1 divided by I plus 1 minus 1 divided by I minus 1. These are the same thing, but how far apart are they? These are 2 apart. If I went back to this problem, how far apart are these? They're 1 apart, right? What did I notice? They're 1 apart, and let's look at our telescoping. How many addition things were left at the beginning? How many were left at the end? 1. If they're 2 apart, how many will be left at the beginning? How many will be left at the end? So what happens is the last 2 of the high numbers, plug in 100 up there, and so you're going to have the last 2 of those will be left and the last 2 at the beginning. And it'll be, if you would go through this problem, the easiest way to look at it, it was just simply plug them in. Actually, I can't do that. I have to start off at 2. Why do I have to start at 2? Because if I plugged a 1 in, what would be the bottom? 0. I'd have a 0. Can't have that. All right, so the first guy is, so this would be equal to 1/3 minus 1 over 1 plus 1 over 4 minus 1 over 2 plus, this was I equal to 2, this was I equal to 3, and then it would be 1 over 5 minus 1 over 3 plus 1 over 6 minus 1 over 4. Notice that they're always 2 apart. And then I'm going to need 2 at the end here, so that would be the last guys. If I plugged in a 99, let's get you over here. If I plugged in a 99, I would have 1 over 100 minus 1 over 98, and then plus, if I plugged in I equal to 100, that's 1 over 101 minus 1 over 99. And what do I notice about my subtraction? Does 1/3 cancel? Yes. Does 1/4 cancel? Yes. Does 1/5 cancel? It would be in that ellipsis, right? Yes. In that ellipsis would be, does 1/6 cancel? Yes, it'd be in that ellipsis. But what's the pattern? Well, the thing on this side cancels with something 2 down. So does 99 have somebody over here in the ellipsis? Yes. Does 98 have somebody in the ellipsis? Yes. All right. It gets down to the question of how much is left. 2 on the left and the last 2 over there. If they're 2 apart, we'll have 2 over here and 2 over here that are kept. Everybody else subtracts. It's up to you to figure out what the 2 of those are. But if you look at it, it's going to be what? Equal to your 2 highest and then your 2 lowest. And that would be your answer. Everything else subtracts. Oh. Yep, yeah, 1 was 100. Can't count. 100. That's that 100. 101. Does everybody care with that? Is that a positive or a negative number? Negative, because 101, 1 101st and 1 100th is pretty small. And then negative 1.5, so. All right. Is everybody okay with what a telescoping sum is? You write down a few terms, you know how many terms to keep, by how far apart they were, and everything collapses. On the other hand, if you wanted to, you can always do the addition method. It's just add the hard way, but that's just a little bit of a problem. All right. The attendance part was exactly, this idea of don't do your sum. How do you add things up without actually adding them up literally, right? You multiply by a constant, subtract things away, and you get your actual sum left over. Now, one of the things that we look at sometimes was sums of like k from k equal 1 to n, and the sum from k equal 1 to n of k squared, and the sum from k equal 1 to n of k cubed. All right, there's lots of ways of showing these. For example, the sum for k. If I would do that one, if we would do this particular problem, the sum from k equal 1 to n of k, this is actually 1 plus 2 plus 3 plus everything up to k. We just simply add that up and say that's my answer. It's supposed to be s. I don't know what it is. But if we would look at that and say, well, this is what Gauss did as a child, is that he was asked to add up from the numbers from like 1 to 100. And so he just flipped it. Yeah, n. He just flipped the order. He said, well, if I added the other direction, the number before n is n minus 1, and the number before that is n minus 2, and then we would keep on going down until I got back down to 1. But that's also s, right? That's still the same sum. If I added up or added down, it would be the same thing. But if I would stack those and add them vertically, what are each of these terms? But that's twice s. Well, how many n plus 1s do we have? There's n of them. I could simply count them. 1, 2, 3, n, right? I can just simply count them as I see it. So that tells me that twice the s is simply n times n plus 1, because that's the definition of multiple additions of the same thing is multiplication, n times n plus 1. So my answer of the sum must be n times n plus 1 all over 2. And so we have our first formula. If I would sum up from k equal 1 to n of k, if you would see this sum, you could just simply write the answer. It's like, quadratic formula. Solve this quadratic. Don't. Just, you know what the answer is, use a quadratic formula. Add this up. Don't. Just plug in the answer. Add up from 1 to 100. It's 100 times 101 divided by 2. So it's 50 times 101, so it's 5,050. Right? Just boom. Just go ahead and use multiplication. We know what the answer is without doing the actual addition. Now, this is also interpreted in a geometric way. If I would look at this and say, could you do this? Well, really, physically, what's going on? I have 1, I have 2, I have 3, and I go until I have n. So that is a 1, that's a 2, that's a 3, and that's an n. On the other hand, we could go the other way. We could have 1, we could have a 2, and that would be n minus 1. And then we would keep on going until I had my, over here, I would have 1 and 2 over here to n. What do I notice? Every one of those is just how many dots vertically. There are n plus 1 dots. And that's a rectangle. So what's the area? The area is equal to n times n plus 1. That's the entire area of this problem. So what would be my sum? How many? I have the exact same number of blue dots as I do black dots, so I would just take the entire area and do what? It's area over 2, which is equal to n times n plus 1 over 2. Hey, look, it's the same formula. So what did Gauss actually do? In his mind, he formed this big giant rectangle. That's what each of these sums mean. So this would be a geometric interpretation of what Gauss did. Just say, look, it's a rectangle. All right. Sums of k squared from k equal 1 to n. All right, there's a couple approaches to this. One way that we could do this particular problem is to say, maybe I can combine some other things that I know how to add, and out of the middle of it will come a k squared. If we already know, can you find this? If we know telescoping and we already know the sum of k. We've already done the sum of k, so it's an answer I know. Well, here's the thing. We're just going to use what is k cubed minus, actually go the other way. What is k, did I use k cubed minus k? Yeah. K cubed minus k minus 1 cubed. Well, if I would add that up as a sum, what type of sum would that be? It'd be telescoping, and I can jump to the answer by using those telescoping techniques. On the other hand, this is also equal to what? Let's do a little bit of algebra. That's k cubed minus what? What is k minus 1 cubed? K cubed minus 3k squared plus 3k minus 1. So using a little bit of algebra, what happens to my k cubes? Cancel, and what do I have? 3k squared minus 3k plus 1. And so what I've learned is if I would sum, since these are equal, summing the left must be the same as summing the right. So that would tell me that if I summed the left from k equal 1 to n of k cubed minus k minus 1 cubed, that must be equal to 3 times the sum from k equal 1 to n of k squared minus 3 times the sum from k equal 1 to n of k plus the sum from k equal 1 to n of 1. What's the only thing I don't know? Can I sum up everything else? Sure. 1 plus 1 plus 1 plus, that's easy. That's n. Right? This, I know. That's n. This, I know. N times n plus 1 over 2. This, I know, because it's telescoping. How far apart are they? They're 1 apart, so I'll keep 1 on the top and 1 on the bottom. So if I plug an n in there, I'm going to keep an n cubed. And then if I plug a 1 in there, I get a 0, and I would keep a minus 0 cubed, the bottom. So it's just n cubed. So everything is known except for the red square. Can you solve it? Yeah. Do some algebra. And what you're going to find is, by algebra, the sum from k equal 1 to n of k squared is going to be equal to n times n plus 1 times 2n plus 1 all over 6. In other words, you have to take that n cubed, you take all those other things, factor it all, and write the entire thing as best as you can. You can see the divide by 3. You're going to have a half. If you divide by 3, that becomes a sixth. So that's where that's going to come from, and everything else will factor. But you have to do algebra to solve for that. All right, that's algebraic. The same thing, we can find k cubed. Now that we know k squared, we can find k cubed by doing what? K to the 4th minus k minus 1 to the 4th. Do a bunch of algebra, and we can get another formula. And if we would do the exact same technique using a telescoping series, we could also find that the sum from k equal 1 to n of k cubed is just going to be n times n plus 1 over 2, the quantity squared. What's interesting is what would be a geometric interpretation of this. So the left-hand side is a sum of cubes, but the right-hand side is a square. So the right-hand side is going to be some large square that would end up somehow being a sum of cubes. This is an old geometric interpretation when you look at this, and it actually ends up being this. That's a 1. So that's a 1, that's a 2, and we get that. And there's a 2. Now we go up 3. Over, 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 and that's a 3, and 3. And I would keep doing this process here. Dot, 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 until I get a, say that's an n. I know that's not the good. 2, 2, 10. And then I go over and down like that. What shape is this? It's a square. How long is the sides? How long is that side? No, it's 1 plus 2 plus 3 plus 4 plus, this is 1 plus 2 plus everything up to n. So what's the length of that side? No. N times n plus 1 over 2, right? We've already done it. So what's the entire area? N times n plus 1 over 2 squared. How in the world is this a sum of cubes? Here's the fun part. Find this number. It's 1 cubed, because it's 1 by 1, right? All right, here's the fun part. This is a 2, this is a 1, this is a 1, this is a 2. That means this is a 1, right? 1 plus 2, so that's a 3. That entire thing ends up being 2 cubed, but you'd have to show it. It'll end up being that you can show this, that this is 1 cubed, 2 cubed, 3 cubed, n cubed. It's up to you to show that, though. You still have to show this. That's the whole key. Show that that shape is actually n cubed. So what's the sum of the cubes? N times n plus 1 over 2 squared. You still have to show it. You also can go online and look up the sums of the squares, and that's a lot different. The sums of the squares actually ends up being, you have the squares, and then you unpeel, you have 3 of them. The sums of the squares physically look like this. There's a square, there's the next square, there's the next square, right? And then what you do is you do another one, and then another one, and then another one. And then we do another group. Take 3 of them. Now obviously we would have ellipsis here going on to n. And what happens is if you would take this and you would peel these apart. If I would take the largest and peel off those numbers, they would end up going here, 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 1, 2, 3, 4, fit exactly right there. Then if I would peel off, like an onion, those and those are 2 3s, it would go there, there, there. There I'd have 2 of them. And then I just have the corners left, which would be here, here, and here, and I would have 1, 2, 3 of those. And it ends up, if he would do this as ellipsis, this side is 2n plus 1. This side is n times n plus 1 over 2, right? Because it's 1, 2, 3, up to n. We need an ellipsis here, right? So what's the area? 2n plus 1 times n plus 1 over 2. But how many of them are actually there? 3 of my sums. So divide by 3, and we get our answer of n plus 1, 2n plus 1 over 2 times 3, 6. But you have to do some ellipsis work to show that. And basically, you take your cubes and start unpeeling one of them, and it fits perfectly, and it forms another big rectangle. Those are the geometric ideas behind these. There's a little bit you have to finish up to actually do it, though. All right, cardinality. We've talked about cardinality before, and we only talked about whether they're finite or they are infinite, which is not finite. So we had the cardinality of a set. Say S is equal to N, which happens to be a natural number. Then we would say S is finite. If not, S is called infinite. So if you would look for the distinct number of elements, and if you get an actual number out that's a counting number, 0, 1, 2, up to whatever, you'd say that this is a finite set. We would also say finite sets are called countable, right? I can count them. They're this number. One of the things that we have an issue with was this idea of not finite. So if I would have, what about the set 1, 2, 3, never stopping? This is obviously, that's infinite. But if it keeps showing back up, and I keep asking, what's its cardinality? It's infinite. What's its cardinality? It's infinite. And we have, all right, can I deal with the cardinality of sets that are not finite? And we could try and ask, what does that mean? Well, one of the things that we could talk about is, what does it mean for the cardinality of one set to be equal to the cardinality of another set? There's two approaches to answering this question. One is you would say, if it's finite, I would say if I have 15 students in 15 chairs because they have the same finiteness, I would say that they're equal. They have the same cardinality. That's one approach. Another approach to do that is, well, what if you don't want to literally count 15 students and count 15 chairs? You don't know how many there are. Could we do both at the same time? Well, what you could do is just simply say, student 1, sit in chair 1. Student 2, sit in chair 2. So one way to talk about the same cardinality would be to go through something and say, if I can make a bijection, A, B have the same cardinality if and only if we have a bijection, a one-to-one and onto rule, from A to B. So let's say we have an example of two finite sets. And so I have student 1, I have student 2, I have student 3, and I have all the way up to student 15. I have chair 1, chair 2, chair 3, all the way up to chair 15. Yes, the cardinality of S is 15, the cardinality of chairs is 15, therefore they have to be equal to each other. But if I could do this, if I could form a bijection between the two, student paired with chair 1, student paired with chair 2, student paired with chair 3, if a bijection exists, if I can come up with a rule that would tell you a seating arrangement that is one-to-one and onto, then they have to have the same cardinality. And so what's nice about this is it doesn't mean count. I mean, it doesn't literally mean find the cardinality. What it says is find a way to pair them. Find a rule that pairs them. So if I can find the rule, I can say, as a byproduct, they have the same cardinality. All right, why is this nice? Well, this is a rule for cardinality that extends to things that are not finite. So I can take things that are not finite. Say, the set 1, 2, 3, 4, 5, etc. That's not finite. How about the set 2, 4, 6, 8, 10? Are the evens finite? No. But can I pair them? What's my rule?
It pairs with its half.
Right, it pairs with its half, right? The even number pairs with half of what it was, right? And so if this is true, there's my cardinal. Is that one-to-one? Is it onto? Does this rule ever stop, and does the rule ever miss anyone? No. And so that tells me that because such a function exists, and I can see it, it's rather easy to do, that tells me that the cardinality of the positive ints is equal to the cardinality of the evens. It's one of those things where we sit there and look at it, but the evens are in the are in the positive ints. And you're telling me that they have the same cardinality? Yes. They're both non-finite. They're both infinite. But they have the same cardinality. It allows them to say that they're both the same type of infinity, same size of infinity. So sizes of infinity get down to a question of, can we pair them? Can you go along and count 1, 2, 3, 4, 5, and does that rule of counting actually count everyone? If you could literally do this for infinity, you would actually count everyone. And so such a thing, when we look at this, says this seems to be a fundamental set. Because it's 1, 2, 3, 4, 5, 6, on forever. And since I'm comparing things, I'm going to go ahead and just simply define that the cardinality of this set is infinite, but I'm going to give it its own type of label. Yes, it's infinite, but it is a cardinality called Aleph null. It's the cardinality of, and really it's the cardinality of the ints, right? Of z plus. Could you count if we would go through this, could I find a pairing between the counting numbers and all the ints? How would you do that? All right, that's a kind of an interesting question. How do I pair z plus with z? This introduces kind of an issue. When I mean pair, that's your rule. Can you make up a rule? And there's a classic game, an intellectual game that goes along with this, and it's called Hilbert's Grand Hotel. The idea of Hilbert's Grand Hotel is z plus represents rooms. And you have a building that has an infinite number of rooms. It's your hotel, you have an infinite number of rooms. And I have two sets of people, the positive people, including 0. This includes 0, right? And the negative people, which are both, I say the non-negatives and the negatives are both infinite. And so I would go through here and say, I have the positive people show up, the non-negative people show up, and then the negative people show up. So you have a building full, that has an infinite number of rooms, not full, they're all empty. And then you have the non-negative lodge people show up. And they all have their numbers. I'm 0, I'm 1, I'm 2. And you notice there's an infinite number of them. And then these negative people show up. I'm -1, I'm -2, I'm -3. Can you give everybody a room? What would be your rule? If I go across the top, room 1, room 2, room 3, room 4, room 5, would I ever get down to the bottom? No, I can't do that. Scratch your head. And say, well, how about this? How about I give you room 1, and I give you room 2, I give you room 3, I give you room 4, I give you room 5, I give you room 6, I give you room 7, I give you room 8, I give you room 9. Now, will that pattern give everyone a room and never miss anyone? Yes. Is that pattern a bijection from z plus to the n's? Yes. So if I have two groups of infinite size show up, both of which are countable, it is still countable. And the word countable just simply means it has the same cardinality of z plus. Kind of interesting.
Could you find a function that creates the bijection between them?
Yeah, what would be the function here? How would you do this? You would say the negative group gets mapped to who? To twice to the even rooms, right? So what would you do? Dear negative people, take your absolute value of your name, multiply it by 2, go to that room. 0, please go to room 1. 1, go to room 3. What are they really doing? Take your name, multiply it by 2, and then add 1, and go to that room. So for the non-negative people, take your name, multiply it by 2, add 1, go to that room. So 1 would go multiplied by 2, go to 2 plus 1. I'm going to go to room 3. 2. 2 times 2, that's 4, plus 1, go to room 5. And so that would be a algebraic rule for them to follow, rather than just simply tapping them on the head. All right, does this work? Kind of an interesting question. And so the idea, again, what does it mean to be countable? If the cardinality of S is finite, or Aleph null, S is called countable. So that's the idea behind countability. All right, let's go to Hilbert's Grand Hotel, and now let's say I have Lodge Group 1, Person 1 shows up. Lodge Group 1, Person 2 shows up. Lodge Group 1, Person 3 shows up. Lodge Group 1, Person 4 shows up, etc. Lodge Group 2, Person 1 shows up. 2 shows up. Lodge Group 2, Person 3 shows up. Lodge Group 2, Person 4 shows up. Lodge Group 3, Person 1. Lodge Group 3, Person 2. Lodge Group 3, Person 3. Lodge Group 3, Person 4. Lodge Group 4, Person 1, Lodge Group 4, Person 2, Lodge Group 4, Person 3, Lodge Group 4, Person 4. Now, if I had a finite number of lodges, all of which have an infinite number of people, how would you count? That's their name tags. How would you count that? Well, one way to count it is just down, right? You could say things like, how about you go to room 1, you go to room 2, you go to room 3, you go to room 4, you go to room 5. That looks like a 5, doesn't it? 6, 7, 8, 9, 10, 11, 12, right? Is that going to count everybody? Sure, go down. What's important is that you go down and it's finite in length. So what am I doing? I'm sending to power multiples of 4 off by 0, 1, 2, or 3, right? So for example, the top groups go off of 1 of a multiple of 4. The second group goes to an off of 2 of a multiple of 4. The third group goes an off 3 of a multiple of 4. And the fourth group goes to a multiple of 4. 4, 8, 12, right, 16, etc. So that would be an algebraic rule. But what happens, though, if you're in charge and you have your hotel, but an infinite number of groups of infinite in size show up? So I don't just have 5 lodges or 6 lodges. I have an infinite number of lodges, all with an infinite number of people show up. How do I give them all a room? Well, what's necessary? I need to walk through them, tapping them on the head to tell them which room to go to, in a way that is always a path that is finite. So I stop and go the other way, and it's always finite. For example, if I go down, I'll never stop. So there I'll never get back to the second person of everybody's lodge. Can you think of a path that goes through here that the paths are always going to be finite in length? They might be growing, but they'll be finite in length. Diagonals, right? What happens if I would go through this thing and go through it and go through, let's give it a nice green. What if I would ski slope this? Go over, and then here, and then there, and then there, right? And I say through, and I go room 1, room 2, room 3, room 4, 5, and 6, 7, 8, 9, and 10. Are these diagonals always finite in length? Yes, they're growing, but they're always going to be finite. Will this pattern of me going down, a better yet would be, let's say that's a rope, right, that everybody's holding, and then I say pull tight. Will everybody get their room? Yes. All right, what do I notice is special about the diagonals? Look at their names. For the guy who's named 1, 1, add those two numbers, what do you get? 2. Look at the guys whose names are 1, 2, and 2, 1. Add those two numbers, what do you get? 3. Look at the guys who are 3, 1, 2, 2, and 1, 3. Add those, what do you get? 4. Every diagonal happens to be, the second diagonal is the sum of the two numbers. The third diagonal is the number 3. It's how many ways can you add to 3? 1, 2, 2, 1. How many ways can you add to 4? 3, 1, 1, 3, and 2, 2. Fifth diagonal. How many ways to add up to 5? 4, 1, 3, 2, 2, 3, 1, 4. The 4 ways of that. And then 6 would be what? 5, 1, 4, 2, 3, 3, 2, 4, 1, 5. Now, last part, what we'll cover for next class now, is this group countable? Yes. What if instead of writing 1, 1, I would have done this? Was that pattern the generators of the rational numbers? It's actually bigger than the rationals because it includes numbers like that are not rational. So if this is actually bigger than the rationals and this is countable, do you think the rationals are going to be countable? Yes. And we'll prove that next class, and then we'll move on to the reals and prove that those are uncountable. But there is no such function that can do this. All right. The attendance is 2.5, number 5. That's it.